The world around us is made up of two things, matter and energy. And in fact, physics is the study of matter and energy and the interactions between them. You can see matter, you can touch matter, but energy is a little more abstract, and so we're going to talk about that now, and we're going to get some of the concepts in front of us. Energy is everywhere. For example, energy is flowing down these electric lines from the generating station to the end user. Energy is taken out of the tank that's underneath the ground beneath the gas station and put into the tank of that car so that the car can go forward. It's converted from chemical energy into mechanical energy in the car's engine. There's the electrochemical conversion of energy inside of a battery. And then there are more colloquial uses of the term, such as children have a lot of energy, which actually has some scientific merit as well. They metabolize more efficiently. They literally have more energy. And so there are a lot of uses of the term, all of which somehow or another have a connection to what we're going to talk about over the next couple of weeks. And we're going to put numbers on energy. Now, if we're going to put numbers on energy, we need to be able to say what we're talking about in terms of a quantity. If I say I have 3 energies, that's a meaningless statement. I need to say 3 watts. So energy needs to be measured in some sort of unit. The watt is joules in SI units, so our preferred energy unit in this course is joules. But when it comes to energy, there are a lot of different units out there that you see being used. There's certainly the calorie, which is a useful quantity, especially for smaller situations, benchtop chemical reaction, for example. And then if you are into imperial units, you might use the British thermal units. All of these things have conversion factors that you can use to go from one to the other. We will stick with joules in this course and increments of it. For example, we might say kilojoules, which means 1,000 joules, or we might say megajoules, which means 1,000,000 joules. So energy by itself is just there. It's just an abstract stuff, but if you harness it, you get something done. And so what matters more than just how much energy there is what that energy does. So this fellow is attempting to go from point A to point B by running. He is spending energy doing that. It's a lot of work for him to get from one point to another. And the farther apart those points are, the more work it is for him to get there. The harder he's got to flex his leg muscles, the more work it is for him to get there. And so work is also a concept. Work is energy getting stuff done. And we can quantify that just as easily as we can quantify energy. Whether you're running or walking, you move forward because your foot applies a force to the ground, and then the ground has a Newton's third law reaction force to that. And so we talk about the force of the foot on the ground or the force of the ground on the foot. They're equal and opposite by Newton's third law. And so that force of the ground on the foot is the force that pushes the runner forward. And he goes forward a certain distance. Let's just call it delta x. I guess essentially the stride of this runner. He's taking steps of delta x. So every time he applies a force to the ground, he propels himself forward a distance delta x. Those two quantities are the quantities that we're going to use to talk about how much work this guy does while running. We need a way to measure work. We need a way to quantify it. So should we talk about, say, the force that's applied? I would rather talk about the force of the ground on the foot than the force of the foot on the ground, even though they're the same quantity, because it's really the force of the ground on the foot that pushes him forward. So let's talk about that. But is that force the work that he does? Well, if he has to apply more force to go forward, which he might have to do if he's not the guy he's dreaming he is, then yeah, you could say more force means more work is being done. But there's more to it than that, because if the place he's going is a shorter distance away, it's going to be less work for him to get there. And so distance has to have something to do with it too. So those two quantities actually go together to help us understand work. Remember when we talked about motion, and the quantity we decided wasn't just the speed, but the mass times the speed, because if you have more of either, you have more motion. And the same applies to work. Only it's not mass and speed now, it's force and displacement. The more force you apply, or the farther you go on that force, the more work you do. So let me emphasize this delta x. It's shown with the yellow arrow in the picture, but what it is really, delta x, is the distance over which the force is applied. So the ground is pushing on his foot with a force of F sub ground on foot over a distance delta x. As soon as he takes his next step, it's a new delta x. So this is the work done during one step of size delta x. He's going to take a lot of steps before he gets where he's going, and you'll have to calculate the work for each and every one of those, but that's the work accomplished every time he takes a step. Work has units of joules. Work and energy are dimensionally equivalent. Energy is in joules, work is in joules. And this is important because work is a measure of energy expenditure. If you spend a certain amount of energy, you can get a certain amount of work done. So if I spend 10 joules of energy, I might just achieve 10 joules of work. If this guy is going to get where he's going to do a lot of work. Overall, delta x is going to be more than just, say, 1 meter. It might be 1 kilometer by the time he gets where he's going. He's going to do a lot of work. What does he need? He needs to eat his Wheaties. He needs energy. And energy comes in two forms. There's the energy of motion, also called kinetic energy. Compare this cardinal and this mosquito. They're going the same speed, but there's a big difference. The cardinal weighs about 10,000 times more than the mosquito. Cardinal weighs about 50 grams. The mosquito weighs about 5 milligrams. 50 grams is 10,000 more than 5 milligrams. So which has more energy, the cardinal or the mosquito? I think it's a reasonable argument that the cardinal has more energy of motion. It's going to take a lot more energy to keep it flying, and it's going to do a lot more damage if it crashes into you. It's going to hurt more. All other things being equal, basically meaning the speed being equal, more mass means more energy. If I have two things going at the same speed, but one of them is more massive, it also has more energy of motion, also known as kinetic energy. Compare the flying cardinal to a standing cardinal. They both have the 50-gram mass. But which one has more energy? Again, I think you can contend that the flying cardinal has more energy. It's kind of in that statement, energy of motion, and one of them is not even moving. So all other things being equal, by that I mean the mass, more speed means more energy. So whether you have more moving mass or just more speed, you have more kinetic energy. And that's a lot like momentum. And so we're going to compare it to momentum, but it's not momentum. It would be a little different. But it accounts for mass and velocity just like motion accounts for mass and velocity. And that's why it's the energy of motion. It'll be next time when I put an equation down in front of you for kinetic energy. The other kind of energy has to do with where things are. I have two scenarios here. Which guy do you want to drop the baseball on your head? The guy at the top of the tall building or the guy at the top of the shack? Yeah, I think it's fairly evident. Oh, we'll just play the animation. It's fairly evident that the guy at the top of the tall building is going to cause more injury when that ball hits you. You don't want that one hitting you. You want to get out of the way of the ball that's being dropped from the tall building. You might not even feel the ball that's being dropped from the shack. What's the difference besides the fact that the ball dropped from the tall building is going faster when it finally hits the ground? That we covered already. The ball that's dropped from the tall building also has more kinetic energy when it hits the head. So if you have a higher drop position, you're going to have more kinetic energy when it hits the head. And kinetic energy, just like work, is measured in joules. And by the way, in events that involve violence, like traffic accidents, kickboxing matches, Mortal Kombat, it's kinetic energy that causes injuries. So I'll put it this way. sort of a summary statement of the idea, that the ball dropped from the taller building has more potential to gain kinetic energy. And hence we say the ball dropped from the taller building has more potential energy before it is dropped. So when the ball is up there in the guy's hand, it has a lot of potential energy, that is potential to gain motion energy. So those are the two types of energy: kinetic energy, the energy of motion, and potential energy, the potential to acquire motion. Potential energy can be there for different reasons. One way that's illustrated here is by having a high altitude, so that gravity has more opportunity to accelerate that ball. You can also have elastic storage. Like imagine this spring and a mass on the end of the spring, and you stretch the spring down, and each of these are different time-lapse photographs, say, of it. You pull it down and then you let go, and of course the spring immediately starts to decompress, and it overshoots, and overshoots becomes short, and then it comes back down. And so as the spring moves up and down, you're storing and then releasing energy from the spring. So when you first stretch the spring all the way down, it's like pulled way down, you have stored up a bunch of potential energy inside the spring. And when you let go, it begins moving and you have kinetic energy. Eventually the mass gets all the way up to the top here. The spring now is compressed, not stretched. And again, you have potential energy. And then the spring uncompresses, and it just cycles and continues. We'll talk about that in a couple of days. Another elastic storage mechanism would be the rubber band in this balsa wood plane. That's also stored up energy, or a rubber band that you use as a slingshot. So store up some energy inside that elastic medium.